All right. Hi, everyone. So my name is Etienne Bernard. I'm the manager of the machine learning group. And today I'm going to talk about the new addition in version 12 concerning the high-level machine learning functions that we also call superfunctions sometimes, which include all these functions to do automatic machine learning, such as classify or predict. So I'm not going to talk much. I guess I'm going to talk a little bit about this function as well. And so the idea is to be able to train machine learning model very simply without having to specify methods or hyperparameters. Like it's very task-oriented. They are task-oriented functions, like classify, and you give a data set, and then you have a model that you can use to classify new data. And I'm going to talk, so it's going to be basically all the new functions in 12 in a large sense. So everything since version 11. So it will include things in version 11.1, 11.2, 11.3, and 12. And it's good to, so if you were there yesterday to the webinar, we only talked about the very, very recent addition because it was only 15 minutes. Now we have more time, so we can talk about all this. So you can see a kind of summary of this new addition in this product page called High-Level Machine Learning, and with some selected example that kind of spans all these additions and updates. So the main novelty in this version, I would say that there's two of them. One is a new automation procedure. So in the past, it was very, how can I say? There's a lot of heuristics, for classify to figure out which was the best method. Now it's a little bit more, I mean, there was also some experimental part, but now it's even more experimental. And it's a smarter automation procedure where you try first on small data sets and you analyze the performance, and then you try a larger data set for the configuration that seems promising, and so on. So it's a bit smarter to figure out what's the best method and what's the best hyperparameter and best preprocessing for a particular task. So that was one big addition since 11. The second big addition is in unsupervised learning. And notably by the introduction of learn distribution, which is a function to learn a probability density. That's actually that's what's represented here in this thumbnail. And this opened up many applications, such as missing imputation. So the idea is when you have a data set with missing values, you can fill in these missing values. Another one is detecting anomalies. Another one is generating examples. And there's also other application that learn distribution unlocks. So it's an important function. We also did other things in unsupervised learning, like new dimensionality reduction method. That's what's represented here. By the way, this was an example of representation of the new automation procedure. For example, this is something, I think it's probably the isomap method. So it's a classic nonlinear dimension reduction method to reduce, to find manifolds in data, but not necessarily flat manifold, also nonlinear manifolds. So if you want, you can see, so today I'm going to present some of these examples, not all of them. That will be too long, but you can see all of them in this page. This first row is about classification and prediction. Okay, so this example, we're actually going to look at it. It's how to train classifier automatically. Then there's an example about all the updates. Some updates we did to classifier measurements. So there's new properties. You can see, let's see, new properties, like you can have a report of how good is your model given a test set. And you can see like a bunch of metrics that include statistical uncertainty. That's also an addition we did, which I think is very nice. I like uncertainties. I hate to see a number and not to know how precise this number is. So each time there's a statistical, estimation done, we put the estimated uncertainty as well. Okay, and there's some other properties, such as you can ask, what are the worst classified examples? And it will pick up those worst depending on, basically it's examples whose probability to be the correct label are the lowest. That's what worst classified examples are. You can say all the examples, okay, you got it, this is a tree classifier. So this will be find me all the confusions between eucalyptus and oaks. More precisely, find me all the eucalyptus that have been classified as oak. So they're eucalyptus, but the model thought it was oak. And you can also do things such as this averaging of, this is binary measure. So this is measure that were originally for binary classifiers, but you can extend it to multi-class by averaging the values. So if you take all the classes, it's a bunch of binary classifiers, and then you can average that. And there's something called micro average, something called macro average. So anyway, it's a bit experty, but it's there. And this compute uncertainty, which is an option that you can set to true or false and get an around object if you set it to true, or just a normal numeric value if you set it to false. So that was another example that I was not supposed to talk about, but anyway, it's an overview. Oops, sorry. This is a new method, gradient boosted tree, that many people like. That example, I won't detail it as well, just a quick overview. It's active classification. So it's the idea that you can, when you have unlabeled data, instead of giving the label, you just give a teacher function. And then the algorithm can choose to give some input to the teacher in order to get the label and learn from it, and can be a little bit smart about what it asks, like what question in a way it asks the teacher. Like you want to ask only the question you don't have the answer to be a bit more efficient. And often the teacher is quite slow to answer, so that's why you have to carefully choose what you give to the teacher. And this example is a very practical example that actually used for real. Maybe, I'm not sure it was exactly in this form, but it's two programs that perform the same computation, but in two different ways. So it's basically computing the Manhattan distance between all the pairs, all the vector pairs in these two matrices. So you have, so it's basically the outer product of Manhattan distance, and you can do it in another way. And depending on the size of the matrices, sometimes the first program is faster, but sometimes the second program is faster. And what I'm doing here is creating, this is just a sampler of matrix size, okay? It's in log space. So, and I'm creating a benchmarking function, okay? That's what's important. So this creates matrices, right? And then apply the first program, measure its time, and evaluate the second program, measure its timing again, and figure out which one was the fastest. Okay, that's a benchmarking function. And then I use active classification with a benchmarking function that is a teacher. Okay, that's a thing that says, actually, program 1 was the fastest, or program B was the fastest. And then I set up a sampler to sample possible configurations, and I run active classification, and it will automatically do its cooking, and like so samples many possible matrices, basically, benchmark which was the fastest, and from that learn what's the best program depending on the input. And you can see here a confusion matrix, so it's reasonably good at picking up which program will be the fastest. And in the end, we end up with just a classification formula. That's why I picked the logistic regression here, because then you can have just a nice formula, and this is an optimized function. It's something that takes the two matrices, compute their dimensions, and then from the dimension with this formula, figure out if program 1 should be used or program 2 should be used, and then just use it. And this is faster than program 1 alone or program 2 alone. So anyway, that was an example of active classification, which I must say, to be perfectly honest, active classification is not the function you're going to use all the time, contrary to classify or predict. Like it's a bit more niche function, but sometimes it can be useful, like in this application. Second row is about dimensionality reduction. So I'm showing, I think I'm going to show that in more detail. Yeah, I'm going to show this one in more detail as well, so maybe I won't talk about it right now. And so this is nonlinear dimensionality reduction and what you can do with them. So I'm going to detail that more later. The third row, sorry, is about synthesizing values. So either synthesizing the complete example, in that case, so it's using learned distribution on images. So it's learning the distribution of this image. Of course, it's very hard to learn from scratch distribution of images. So in that case, we just use a simple method, like the multinormal method. And you can see sample of this distribution that are clearly you can recognize it's not real images. So it captures some statistical property of the image, but not too much. Because the method was rather naive here. But the goal of this example was not to have real image, but just use that as a tool to create some sort of random image and do art with them. So here you have random image, and then there's a little bit of post-processing to add a little bit of style to this random image. So basically create a art generator, like sort of abstract art generator, using learned distribution as a tool. But maybe a more practical application is not to generate the entire example, but generate part of it. So which means filling in missing values. Which mean so the goal is if you have to learn the distribution of data, and then being able to condition, let's say you take this example and the gray part are not gray color, it just means it's missing. Okay, it's just missing values. And so you can use the distribution to condition on the known values and sample missing value from this conditional distribution. So in a way, it's guessing the missing value that makes sense given the rest of the image, given the context. So this I'm not going to show this example, but I'm going to show these two in more detail. So how to filling in missing values. What we say, we call it synthesize missing values. Okay, and the last one is mostly about anomaly detection, so other application of learned distribution. So basically, I don't think I will show this one. So let me present it quickly. Actually, I was showing that in the webinar yesterday. If you want to, there's probably the video online somewhere. But the idea here is, again, to learn the distribution of images. Actually, it's implicitly learned. So it's used in anomaly detection that learns the distribution and uses distribution to figure out when an image is anomalous or not. And in that case, we are corrupting an image more and more and more. And we are measuring what we call a error probability, which is a number that indicates how anomalous, given a distribution, is a given example. So you can see as the example gets more and more corrupted, this error probability is going down. Okay, so that's an overview of what's new in 12. And now let's dive into some specific examples, do a little bit of live coding. So I'm going to start with automatic classification and show you a bit how how it works. So let's load a data set. It doesn't really matter what it is. This is just a bunch of numbers. Actually, let's have a look. Yeah, so it's a bunch of number and a class. Okay, it's actually trying to recognize what letter it is according to some property of I think, you know, handwritten letters or something like that. It's an old data set, but that's not the what's important. It's nice to show the automation. So I want to classify. Okay, I want to train a classifier on data sets. So I just do classifier of data. That's it. It's an automatic function. I don't have to put anything else. I can put other things like the method or preprocessing or whatever, or hyperparameters, but I don't have to. And you can see this panel, this kind of training progress monitor panel that shows kind of a progress bar, time elapsed, how many examples have been used, the current best method. Let's run it again. So we can see again, so current best method is nearest neighbor here, the current loss function. Okay, you know what? I'm going to show you right now this time goal. This to tell, I want to wait, I'm like, try to take 20 seconds to do your computation. Okay, so you can see the learning curve happening here. So this is the loss function, which is the log likelihood. You can also see the accuracy that is progressing. And here you can see all the experiments that have been done so far that are updated in real time. So basically what this procedure is doing, as I was explaining before, is that it has many possible configuration. Okay, let's run it again. So it tries, for example, let's look at this one, with a logistic regression and these hyperparameters, or let's try nearest neighbor with these parameters, or let's try, what was this one? Another logistic regression with different hyperparameters, or decision tree with different hyperparameters. So it's trying to figure out which one will perform the best on the full training set, which is like here. And for that, it performs experiments. Let's do it again. Experiments on small training set first. So let's say only 10 examples. And then depending on how successful they are, some of them will be promoted to be trained with a larger training set. So it's a bit like what a data scientist would do, like try some small data sets, see what works, and what works, I give it more data because it takes more time to train on larger amount of data. And that's how you can find in an efficient way which is the best method to tackle this specific data set, because all data sets, some methods work well on one data set and not well on another data set. So that's the idea. So once you have a classifier, you can ask information about it, which is new as well, by the way. So you have a sort of report of how good is the model, including, so okay, you have its accuracy, so it's estimated accuracy. You have the method used and the hyperparameter used. Also, how long it takes on your computer to evaluate the model for one example, how long it takes to evaluate when you give a batch. This is cool because this is really on your computer. When you compute information, and actually it should be a different number if I do it again. Oh, it's kind of the same number. Oh yeah, it's a little bit different. It evaluates, when you do information, how fast this model runs on your computer. So if you give this model to somebody else, it's going to be a different number here. The model memory, how many training examples used, and oh, I can see some question. How does the classifier choose what pipeline to use among the different experiments done? I mean, what kind of optimization process use? Okay, it's not Bayesian optimization. It's basically improved random search. So it has many configurations at first, let's say 100, which are based on heuristics. So they're not completely like uniform random. Depending on the data, there's a bit of heuristics, and that's what it believes configuration could perform well on this data set. And it's very cheap to train on small examples. So you can have a lot on small training set. So you can have a lot of configuration then. And then the whole goal will be to find, given this pool of initial configuration, which one is the best here. So yeah, that's how we pick the configuration to start with. Yeah. Okay, and so you can see the training times, the learning curve. So, okay, one nice thing about this procedure is you have a learning curve. I think it's the main added value. Because you did this experiment on all these different training set size, it gives you, so this is basically what was the best model with 100 example. What was the best model when we trained with 600 example? What was the best model when we trained with whatever, 2000 or something examples? And this learning curve is useful to answer the question, should I, like, what can I expect if I give, let's say, 10 times more training data? And so let's say you go, so, you know, you cannot predict exactly what you will have if you give 10 times more data, but at least if it's completely plateaued, you know that it's useless to get more data. Like you kind of reached, you know, so some sort of information theoretic limit, or maybe just the model are not good enough to capture what's missing. So I think having this learning curve are a big added value. And you can also review, that's a second added value. You can review the experiment. And for example, the model, for some reason, decided not to pursue gradient boosted tree here, even though it was the best here. So it tries always to predict what would happen in the full training set. So maybe that's why it didn't got picked, because it was predicted for some reason to be not so good on the full data set. But it also, it's also working in time constraint, right? Here, 20 seconds. And even when I don't put a time constraint, it kind of try to constrain itself, which actually it's quite interesting when it's automatic how it works, but maybe I shouldn't detail that. So maybe this model was too heavy, took too memory, and so the automation procedure decided not to pursue it. But because you have access to this, you can decide, oh, actually, you know what, I really want to know what this gradient boosted tree would give. And so you can, you know, set, let's see, a method, like you could do method goes to, and you put a gradient boosted tree, actually it was there, and you can start setting the, so boosting method gradients. Anyway, I'm not going to do it, it takes a bit of time. But you can review this and kind of, you know, it's a bit of an interactive procedure with the machine. So I like a lot that it's a bit, how do you say, open, it's a bit, I can't find the word. But anyway, that the machine tells you what happened. And the other things that you can stop at any moment. So that's a useful features of this new automation procedure. Okay, you can also method option. Okay, that's something useful because that's all you need to retrain the model using only the winning configuration, which is this one. So if you do classify data, and you can just, you know, copy paste that or whatever, and that's what you need to retrain much faster. So if I do something, it's going to be basically the same thing, but it's going to be direct because you didn't have to search for the best configuration. You can ask for just the learning curve. Okay, fine. You can ask for the accuracy. Great. With this uncertainty estimation. Okay, let's do a little bit of test, and actually let's test if this accuracy is good by testing on a test set. So this is also on test data, because you have some sort of cross-validation happening inside. You can get a fairly, you know, unbiased estimate of what what accuracy on or whatever measure is. But it's always nice to just have a complete held out test set. And oops, sorry. Okay, that's a test. That's test data. Let's run classifier measurement. So first argument is a classifier, second argument is a test. Then we want to know the accuracy, and we're going to compute its uncertainty. And normally it should, oh, that's interesting. We were kind of pessimistic on the test set, it has a higher accuracy. Well, that's good. That's good. Did I? Wonder. Oh no, it has more on this one. Oh, that's interesting. It has. Oh, it's because we retrain it, and maybe because it didn't have to do many. I wonder. Like the first time, we were actually more on point about what the accuracy was. Okay, and okay, you can also, so already use time goal, you can put just number of seconds, or you can put a quantity by doing control equal, right? So if you do control equal, then you can type, whatever you want, 1 hour, and it's gonna run for 1 hour. Another big added value of this new procedure, before you couldn't control how long the training would be. And so if you put a long training, then it's gonna try more configurations. So there was a question before about what configuration is chosen. If you put 1 hour, it's going to have time to try a slew of them, and in the end, you can be pretty confident that the best one, that you identify the best one. Okay, so I think that was it for the new automation procedure. I should mention that predict use the same automation procedure, learn distribution, and basically all the new high-level like machine learning super functions use this new automation procedure. But we are kind of retrofitting little by little the older functions. So currently, dimension reduction that I'm going to show right now does not use this automation procedure. There's also other reason for that. It's that it's a bit hard to define a good loss function for dimension reduction, especially when the number of dimension is not specified beforehand. Like it's a bit unclear, like, do you prefer something that preserves more information and in different dimension 5, or something that preserves less information but is in dimension 3? It's not really clear. There's not a universally accepted loss function for that. So, but that's one of our goals, to kind of retrofit even this a bit harder to automate function and to use the same procedure. Okay. And also clustering. Clustering is something that I think we are missing a good automation procedure. We would have much better performance if we use something like that, and hopefully we can retrofit that soon. Okay, so let me show you now some nonlinear dimensionality reduction method. So this is the classic toy data set, which is definitely not a real-world data set, but it's more of an educational one. It's called a Swiss roll. So you can see this 3D point, but clearly that seems to lie on a 2-dimensional manifold. And so the goal of dimensional reduction, let's say if I reduce this data set from dimension 3 to dimension 2, will be to uncover this manifold. So I'm going to use the isomap method that has been added. So there's a few, let's look at documentation. There's the few new methods that have been added. Let's see, the nonlinear one. So there's isomap, that's a nonlinear one. There's local linear embedding, often called LLE. We also have an autoencoder method, and TSNE, which stands for T-distributed stochastic neighbor embedding algorithm. Embedding. That is mostly used for reducing in low dimension for visualization purpose. So usually this one is not much used as a preprocessing, contrary to the other one. Okay, so I see some questions. That is high-level automation also exists for neural networks? No, it doesn't. And that's a very interesting question. Yeah, you say, okay, in the sense that the Wolfram language automatically look for architecture. Yes. That makes total sense. That's something we could add at some point. I hope we can generalize that as much as possible. Currently, it's quite tailored for these high-level machine learning functions. But that's something I believe we should provide, kind of generic tools where you can set, when you can define in some way the space in which you want to search, and then that your metric and that automatically kind of search the space. And so for neural networks, it might not be the number of examples you give to the network, but it might be how long you train the network. That's something I believe we should work on at some point. But the answer is currently no. It's only for these high-level machine learning functions. So for now, you would be resolved with a bit of gut feeling and random search. Random search is actually, random search is decent. Much better than grid search for sure. And what else I want to say? Oh, and you also resolve in not inventing your architecture, because it happens that like finding a new architecture yourself is often a very hard task. So the best is to use a neural network that exists already in the neural network repository. You probably know, this net model stuff, and you have a bunch of networks, and like CapsNet, and use that and do some minor modifications. I think that's usually the idea on how to use neural networks. Like beyond that, it usually gets tough. But I mean, if you're an expert, I totally understand that you want to do your own networks. Okay. So let's continue. So this trained the reducer. And now I'm going to create a bunch of two-dimensional points and invert the reducer. So I'm taking this point and I'm inverting them to see where they lie on the original space. This basically will show the manifold that the reducer found, and hopefully it's going to look like this manifold. And then I'm going to plot. Then I'm going to plot the original point, but I'm going to color them depending on their reduction. So in a way, by the way, for the more mathy of you, this is a bit like learning a parametric surface. Like there's this reducer. I mean, the inverse reducer is a parametric surface. So that's what we are looking here. We are looking at the surface parameterized by the reducer, and it takes a bit of time. Okay, so good. It looks like that's funny. We went a bit on other region of space, and okay, that's what it learned. And we can do list point plot 3D just to show the. Okay, so here we can see the parametrization of this manifold. You can see that clearly it learned to parameterize this direction. Actually, we just look at one of the parameter we took first here. So it is a parameter that encodes the position along this this direction. All right, so I'm going to accelerate a little bit. Actually, accelerate. Maybe I won't show everything. Okay, no, still 4 more examples because it took more time than expected. Feature space plots. Okay, very simple new function. You just have data and you just apply feature space plot to the data. And this allows you to visualize your data set because each data element, each data example are projected in this 2-dimensional space. But it's not a random projection. It's a learned projection where things that look similar for some reason, that are similar for some reason, are put together. And actually, so this is just a bunch of paintings, and you see that all the Picasso have been put together here. All the Van Gogh have been put over there. And all the Aboriginal arts are put like together here. And I think there's one here, but it seems like that's not a real Aboriginal art. Huh? What is that? I don't know. It's a very pixelated one, at least. I don't really know what that is. Okay. So, and so you can apply that to any data you want. So it's a nice way to visualize your data set. And it's used dimensionality reduction, and it uses a TSNE method. Okay, so you can also do that in 3D, by the way, feature space plot 3D. And by the way, it uses TSNE, but it also uses a nice preprocessor for images that is based on neural network. So this automatic machine learning function, the goal is not only to find the best method and best hyperparameter and best preprocessing, it's also to kind of know about classic data already. So if you give it image, it will directly preprocess them to extract relevant features for images. Usually, I mean, actually currently with a neural network that has been trained to recognize images. So, and same if you give text or if you give sound. If you give sound, there will be a neural network processing the sound that has been trained. I think it's a network, actually I know it's a network of audio identify. And the network underlying audio identify is used to preprocess the data. And that gives much better performance. For example, for images, you can train a classifier with maybe just, oh, did I share? Oh, sorry, there's been some technical problem here. Okay. You can train an image classifier with, let's say, 20 images instead of millions, or instead of thousands, because you have this smart feature extractor that kind of already know about the images. So, and that's what's happening here as well. Okay, so FeatureNearest is also use this preprocessing and nonlinear dimensionality reduction to create some sort of smarter let's say nearest like search system. So let's say I have a bunch of sneakers. I could do feature space plot. This is just for visualization. We're not going to use result afterward. And probably, okay. So we can see that already it found some, you can see that it found some similarities, even though they are of different colors. Clearly, these similar looking sneakers have been put together, and similar looking sneakers have been together here. And so this is only in 2 dimensions. We don't have to reduce to dimension, but we can use this sort of reduction to create a search system, like doing the search in this feature space, which is going to give much, usually a better search system. So let's just use FeatureNearest. So this is reducing the sneakers in low dimension, first preprocessing them with a neural network. And now if I give new sneakers that were not in the training set, and I can say, okay, according to this nearest function, what is the closest sneaker to this one? What is the closest to this one? What is the closest to this one? And it will give something. Okay, so the closest to this one is this one. The closest to this kind of high, I don't know how to call that, is this sneakers. And it's interesting that they don't necessarily are close in terms of pixel distance. So clearly these have different colors. These are in different directions. This one even is gray on the background, while this one is white. But this FeatureNearest is it's a bit more of a semantic distance that we created. Okay, that's also a byproduct of this dimensionality reduction and feature extraction. Synthesize missing values, a very recent function. So let's show an example directly. So we have a data set and you have missing values and you would like to fill in these missing values. But of course you don't want to fill, you want to fill something that makes sense. So this is the moons of Jupiter. So you have the radius and you have the mass. And clearly the one that have a big radius have a very big mass. While the one that have a small radius, only 18 kilometers here, have a very much smaller mass, actually, 1 million times less than this mass. So yeah, you want to have mass that makes sense here. So let's do synthesize missing value, and that's exactly what synthesize missing value is doing. So you saw this little pop-up before. You can see it again. This is actually learned distribution, this training. And so what it does is that it learns the distribution for this data set, and then it conditions the distribution on the known values and sample distribution that are missing. So if I do 2 synthesize missing values, it will be different values that are filled in because of this sampling process, or actually because of the modeling process as well. But anyway, you can see that here they have small radius and it's also small mass, so that kind of makes sense. You can also choose the method of learned distribution that you're going to use underneath. You can say, I want to use a multinormal method. And okay, right. And you can also tell, actually, I don't want you to sample from this conditional distribution. I want you to find the most likely missing values given the known values. And this is by specifying this evaluation strategy. You say mode finding instead of random sampling. And here it's going to be the mode. I mean, okay, you don't see much difference, but I'm going to show in the next, actually, let's show another example, a bit more educational, where I'm going to learn. So, okay, here I use directly synthesized missing value. This time we're going in 2 steps. We're going to first learn the distribution and then use that to synthesize missing values. So that's the data. Oh, sorry, where am I? Okay, I'm here. That's the data we want to learn from. I'm learning the distribution of this data. Then I'm going to plot the probability density function of this distribution. So maybe I should spend a little bit of time just on learn distribution. This is this new super function I was telling you about. So it's also completely automatic. Actually, if I do information of the distribution, I can see the similar panel that you saw before for classify with the best method, so the kernel density estimation that's been found with a Gaussian kernel type. Method is fixed. It means fixed radius as opposed to adaptive radius. There's 4 neighbors number and a kernel size of 0.15. So that's the method. And you can see all the experiments that have been done. Okay, you can't see much because some very bad experiments have been done apparently. So it kind of killed this graph. Sometimes they're removed from the graph, but for some reason, it decided to keep it there. Okay, and the learning curve. So that's the probability density function of this learned distribution. And then we can say, okay, from this distribution, I want to synthesize missing values. So the first argument is a distribution. And the second arguments are the data with missing values. So here I'm saying that the X value is 5.5 here. And the Y value, I don't know. So it means it has to pick something, it has to find a point along this line that I'm showing with the mouse here. And I specifically chose 5.5 because then it's kind of a bimodal, it's kind of 2 choice. It could either filling the Y value with something between 1 and 2, or it could fill the Y value with something between, okay, let's say 3 and 6 or something like that. So this time it picked 5. This time it picked 1.2. Okay, so that's the sort of things. And so I can, for example, grab 1,000 of them. I'm going to show you 10 examples of this imputed. And I'm going to show on this graph, 20 of this, kind of reconstructed, like imputed example. And you can also show the histogram of this Y value. So sometimes, as you see, it's a bimodal distribution. So this is really the conditional distribution of learned distribution. So it's conditioned on X equals 5.5. And we can, as we did before, say, I don't want a random sample, but actually want to find the mode. So what is the most likely? So apparently when X is 5.5, the most likely is 3.9. And I can show you where 3.9 is lying. So apparently this is the mode. I don't think it's quite exact, I think if you go a little bit upper, it's approximation of the mode as well. Like you cannot have, I mean, you can, but sometimes it takes too long to have exact mode, but some detail that is worth mentioning. Okay, so that's for synthesizing missing values. Now I'm going to talk about anomaly detection, and that's the last one. And we seem to be on time. By the way, you can continue to ask questions on the chat. I don't see all of them. Like somebody is transmitting the important one, I believe. But I'm happy to answer them while talking, and I can also spend time answering them at the end. Okay, so anomaly detection. So here the idea is, from this data set, figure out which example are anomalous. All right. So it's a bit like, it could be called outliers as well. So there's a function called find anomalies that you just run, and it figures out possible anomalies. So the way this function works is that it tries to, how to explain that? So it tries to learn the distribution of the data. I mean, the goal is to actually learn the distribution of non-anomalous example. But since it doesn't know which one are anomalous or not, it's a bit of a chicken and egg problem. So it does a sort of cross-validation, like training, let's say training on half the data set, learning a distribution, and then using that to estimate from the other part of the data set which one are anomalous. And the definition of anomalies is, an anomaly is an example that has a very low probability density. Okay, so something that is like statistically different to the other examples, and the other examples are defining by the distribution that is learned. So okay, that's why, and you can see also a panel here going on. So it's learning a distribution and finding anomalies. Actually, you can see it's a different number of anomalies. It's because of this automation procedure. Unfortunately, it's non-deterministic because it tries many like the timing are taken into considerations. If something is too slow to train, it's not going to use it to retrain it on larger data set. And that's why, depending on what's happening on your CPU, it's going to give different results. Also, I think it's not the best data set to show that because they're not really anomalous. Anyway, so it's kind of a hard finding anomaly task. So okay, this one I've been found anomalous by find anomaly. You can also call something called anomaly detection, and this will return an anomaly detector function that can be used to like a classifier. It's this one, so this is two normal examples, but I'm going to add, you know, let's be a bit crazy for this example. It should return, okay, this is an anomaly, and this is not an anomaly. Okay, it returns true for this one and false for this one. It's a binary classifier. And what did I want to do? No, that's already, oh yes. What we can do as well is look at the error probability. So I didn't spend time talking about this, but that's a bit what's defining anomalies. Let me go, oh, we almost, time is almost up, but I think it's very interesting. So error probability is a function to compute how much of an outlier is an example. So in this simple case, let's use it here. Let's say normal distribution. The question we ask here is, given this normal distribution, how likely it is to generate a sample that is more rare than this value? And rare is defined by the PDF. So what is the probability to generate a sample that has a lower PDF than this value has? And in that case, it is this thing, which is 0.027. So it's pretty low probability. There's only 0.3% of chance to have an event more extreme than this one. So for this case, it's the same as this sort of double-tailed p-value computation. But this concept generalizes to arbitrary dimensions. So for any distribution, you can always ask, what is the probability to sample something with a lower density? And anomalies are defined by an example whose error probability is lower than a threshold. And this threshold can be set up with the option. Sorry, I have a bit of a supporters at home. Can be defined by the acceptance threshold option. So if I say, let's be a little bit less crazy. So let's say 10 centimeters. Okay, it's still, let's say, I don't know, 4 centimeters. Okay, or 7. Okay, great. Something like this. This says that for this example, and let's only pick this example. We don't need to be bothered by the rest. This example, there's only 1% of chance, 1.5% of chance to have something more rare than that. So depending on the value of the acceptance threshold, it will be considered as an anomaly or not. So if I say acceptance threshold goes to 0.02%, it's going to say, yes, it's an anomaly. By the way, it was this example there. So should have 2 features instead of 0. What is going on? What is going on? Didn't type that right? Formatting problem? No, okay. Acceptance threshold, so 0.2, it should say, yes, it's an anomaly. 0.2, but if I put 0.01, it will say, no, it's not an anomaly anymore because the threshold is lower. So that's how we define anomalies. Okay, and actually I can show you, yeah, this will show, I'm thinking it's going to take a little bit of time, but basically this plot with also a contour plot for the, it's a contour plot of error probability of data. So it's kind of the same as a contour plot of the distribution. It's kind of the same as what we show here, but this time it's for error probability. And it also shows the outlier boundaries. Oh wait, this was the anomalies of the previous. This was the anomalies of fine anomalies. So with the detector, it finds less anomalies for some reason. Anyway, that's fine. So forget about this red sting, but anything for this detector, everything that is in this region is considered anomalies, and everything that is in this region is not considered as an anomaly. Okay, that was it for anomaly detection, and that was my last example. So if there's some additional question, please let me know. Otherwise, thank you for attending. All right, no more question apparently. Well, thank you for attending, and I hope you will use this. Let me know. Some are quite experimental, like the anomaly detection is experimental. Things like missing value and learn distribution in general is our experimental function. So we might do some design tweaks, like design changes. They might not work as well as completely finished functions. So please let me know if you have some problems or some comments, and also let me or let us know if there's a particular direction you would like us to take concerning machine learning superfunctions. I think we start to have the whole spectrum covered with classification, prediction, all this unsupervised learning thing. There's still something we are missing, reinforcement learning function, for example. But since they are less used, we haven't put it as a priority yet. But anyway, if there's things that you think we are missing, let us know. That's very valuable to know. All right, thank you very much. Bye-bye.